Hello, and welcome to today's session. This session focuses on the learning outcome LO1, Understand Optical Isomerism. In this video, we will explore why optical isomerism is a crucial concept in chemistry. You will be introduced to the fundamental principles of optical isomers, their distinctive properties, and their importance in real-world contexts. Particular attention will be given to their role in pharmaceuticals, highlighting how non-superimposable mirror images can have significantly different biological effects. Optical isomerism is a type of stereoisomerism where molecules have the same formula but differ in three-dimensional arrangement. These molecules are non-superimposable mirror images, much like left and right hands. The presence of a chiral center, a carbon bonded to 4 different groups, is essential. If 2 groups are identical, the molecule isn't chiral. This fascinating property leads to the formation of enantiomers. A chiral center in a molecule is a carbon atom bonded to 4 distinct atoms or groups. This asymmetry allows the molecule to exist as 2 enantiomers, which are non-superimposable mirror images. Enantiomers have identical physical properties, but differ in how they interact with plane polarized light. They rotate light in opposite directions, termed dextrorotatory and levorotatory. This optical activity is a key characteristic of enantiomers. Normal light vibrates in all directions, but plane polarized light vibrates in one plane. Enantiomers affect this light differently. One rotates it clockwise and the other anti-clockwise. These rotations are termed dextrorotatory and levorotatory. The signs plus and minus don't relate to structure but are measured experimentally. A racemic mixture contains equal amounts of both enantiomers, resulting in no net rotation. Optical isomerism has significant implications in biological systems. Enzymes and receptors are chiral, making one enantiomer beneficial and the other potentially harmful. In pharmaceuticals, one enantiomer of a drug may be therapeutic, while the other could be inactive or toxic. This emphasizes the importance of optical purity in drug development. Understanding these nuances is crucial in pharmaceutical chemistry. To identify optical isomerism in exams, look for a carbon with 4 different groups. This indicates a chiral center, suggesting optical isomerism is possible. Draw 2 mirror image structures and ensure they are non-superimposable. Use key terms like chiral, enantiomers, and plane polarized light accurately. This checklist helps in recognizing and explaining optical isomerism. Optical isomerism arises when molecules with the same molecular and structural formulas differ in spatial arrangement. A chiral center, usually a carbon bonded to 4 different groups, is essential. This asymmetry leads to 2 non-superimposable mirror images called enantiomers. They interact differently with plane polarized light, showing optical activity. These isomers are crucial in biological systems. Alkanes are saturated hydrocarbons with single carbon-carbon bonds. They follow the general formula CnH2n+2. Alkanes do not easily undergo addition reactions due to their saturation. Examples include methane, ethane, and propane. These compounds are fundamental in organic chemistry, forming the basis for more complex molecules. Alkanes are named following IUPAC rules, based on the longest carbon chain. Prefixes like meth, eth, prop denote the number of carbons. The suffix -ane indicates an alkane. Examples include methane for 1 carbon and ethane for 2. Proper naming is essential for clear communication in chemistry. Alkanes are derived from crude oil through fractional distillation. This process separates hydrocarbons based on boiling points. Alkanes serve as fuels due to their high energy release upon combustion. Common uses include methane for heating and propane in LPG. Understanding their production and uses is vital for industrial applications. Cracking breaks down long-chain alkanes into smaller, valuable molecules. This process involves high temperatures and catalysts. It produces short-chain alkanes and alkenes, essential for fuels and plastics. Alkanes, unsaturated hydrocarbons with double bonds, are more reactive than alkanes. Their general formula is CnH2n, and they are crucial in chemical synthesis. Geometric isomerism occurs in alkenes due to restricted rotation around double bonds. Each carbon in the double bond must have two different groups. Isomers are classified as cis or trans based on group positions. These isomers exhibit different physical properties, like boiling points. Geometric isomerism adds complexity to alkene chemistry. Alkenes undergo addition reactions due to their reactive double bonds. Electrophilic addition involves breaking the pi bond and forming new single bonds. This reactivity allows alkenes to form polymers through polymerization. They also react with halogens, changing bromine water from orange to colorless. Understanding these reactions is key in organic synthesis. Haloalkanes form when alkanes react with halogens under UV light. This free radical substitution involves initiation, propagation, and termination stages. Haloalkanes are named with prefixes like chloro, bromo, and fluoro. They contain carbon-halogen bonds, making them reactive in nucleophilic substitution. These compounds are crucial intermediates in organic chemistry. Alcohols contain the hydroxyl group and are classified as primary, secondary, or tertiary. They undergo oxidation to form aldehydes, ketones, or carboxylic acids. Alcohols can also be dehydrated to form alkenes. Their reactions with potassium dichromate indicate oxidation by color change. These versatile compounds are essential in various chemical processes. Aldehydes and ketones contain the carbonyl group, with aldehydes having it at the chain's end. They form by oxidizing alcohols and can be distinguished using Tollens and Feelings tests. These compounds undergo nucleophilic addition, with reduction forming alcohols. Their reactivity and formation are central to organic synthesis. Carboxylic acids contain the carboxyl group and form by oxidizing alcohols or aldehydes. They are weak acids, partially dissociating in water. Acyl halides and acid anhydrides are more reactive derivatives. These compounds undergo addition-elimination reactions with water, alcohols, and amines. Their reactivity is crucial in producing esters and amides. Esters form in a condensation reaction between carboxylic acids and alcohols, known as esterification. This process requires a catalyst like sulfuric acid and heat. Esters are known for their sweet, fruity smells, used in food and cosmetics. They are also solvents in various applications. Understanding ester formation and properties is vital in organic chemistry. Amines are derived from ammonia with hydrogen replaced by alkyl groups. They are basic and used in dyes and pharmaceuticals. Amides form when acyl halides or anhydrides react with ammonia or amines. Amides are less reactive and important in proteins. These nitrogen-containing compounds play significant roles in organic chemistry. In conclusion, this video highlights how a deeper understanding of this field underpins significant advances in both pharmaceutical development and materials science. Such knowledge not only enhances current applications, but also drives innovation across multiple disciplines. Continued exploration of this area offers valuable insights and holds strong potential for future scientific and technological progress. If you have any questions, please WhatsApp us at 07484361-688. Our team will be delighted to assist you. Thank you for your attention, and see you at the next session.